Okay, this is the final set of questions for chapter 15. These are questions 15, 20, and 24. Kind of random, but I think those are kind of like the easiest ones of the rest of the chapter. So starting with 15, the combustion of 0.5865 grams of lactic acid raises the temperature of a calorimeter from 23.1 degrees Celsius to 24.95 degrees Celsius. Let me just fix this real quick. Calorimeter. The heat capacity of the calorimeter is 4.812. Calculate the molar heat of combustion of lactic acid. This one, we're going to use a slightly different formula than what we've been using for heat. So if you remember, for heat capacity, we were using Q equals, come on, man, mc delta T, where m was mass, c was heat capacity, delta T was temperature. In this case, we don't have mass, but we got moles, so we're just going to get rid of the mass. That's fine, just like that. And then we're going to be able to use heat capacity times delta temperature to get the heat, just like that. So we're going to use 4.812. So Q equals 4.812 times change in temperature, 23.10 to 24.95. 24.95 minus 23.10. Okay, get 1.85. Okay. There we go, 4.812. And we should get 8.9022. Okay, so this is basically the one we want to use if we've got the moles of something. If you've got the mass, then you use the mCAT. I shouldn't say A because it's not really A, it's delta T. So mc delta T. Now, the other thing that we need for this one is the moles, right? So they give us 0.5865 grams of lactic acid, 0.5865 grams of lactic acid. Now, let me just, man, I should have looked this up beforehand. Molar mass of lactic acid. And that's going to be 90 grams per mole. So here's a 1 times 90 grams for 1 mole. Okay. It's going to be a small number here. Let's work that out. 0.5865 divided by 90. 0.00651. 2. Let's say 2. So 0.00652. We gotta round up. Okay, and then you just put your heat, 8.9022, over your moles, 0.00652. 8 divided by 0.008 equals 1,000. Oh, what was that? 1,366.066. And there you go. Okay. Next, consider the following reaction. 65 grams of, 2 aluminum plus Fe2O3. They react, and we end up with 2 iron, and 1 aluminum, Al2O3. The delta H of that is negative 852 kilojoules. One thing about this question, I'm not gonna lie, I did it, I worked it out, didn't really have too much of a problem, but when I looked it up, I found a different answer. So we're gonna have to ask the professor about this one before we actually go ahead and take that test. So right here, let me just show you guys what I did. Hopefully this is right. If it's not right, then I'll just be like, guys, ignore this question. So, or maybe when you guys watch this video, you'd be like, man, this guy did it all wrong, and text in the group me and correct us. Okay, so we got 65 grams of aluminum reacts with excess ferrous oxide. So right here, we're only worried about the aluminum. And the heat released is used to warm a 50 kilogram block of brass, initially at 20 degrees Celsius. What is the final temperature of the brass? The specific heat of brass is 0.37. All right, so remember how in the last video we talked about going from from grams to moles, and then moles to heat, kilojoules. Well, that's what we're going to do here in the first step. We're going to go 65 grams of aluminum to the moles of aluminum. So 65 grams of aluminum. Okay, times 1 mole over the molar mass of aluminum. Okay, so 1 mole of aluminum is actually going to be 26.98 grams. 26.98 grams. All right, so there we go. Grams cancel out. Now we got moles, and then we have to go from the mole of aluminum to the kilojoules. So here we see that negative 852 kilojoules corresponds to 2 moles of aluminum. So we got to put 2 mole of aluminum, because that's how much we have in our equation, in our reaction. Negative 852 kilojoules. And there we go. So moles cancel out. All right, so we got 65 divided by 26.98. That gives us 2.41. Let's use 2.41. So 2.41 times 852 over 2. So let's do that one times this. Sorry, negative 852. Okay, because we got heat released. So we lose heat, that's going to be a negative number. So 1026.66. All right. So this is going to equal negative 1026.66 kilojoules. All right. So if this is 1,000 kilojoules for our other formula, which is Q equals here mc delta T. We're going to need joules. So 1,000 kilojoules times 1,000 joules. So we got to go from kilojoules to joules. We just got to multiply times 1,000 because 1 kilojoule is 1,000 joules. So we have, my goodness, 1,026,660 joules. Yeah, 1,026,600 joules. I hope that's what I said. Okay, joules, and that equals mass. We have 50 kilograms, but remember, we have to go from kilograms to grams. So that means that if we have 50 times 1,000, right? Yeah, kilos, 1,000. Okay, that means we've got 50,000 grams. Okay, equals 50,000 grams times the specific heat of brass, 0.37. Okay, and they're wanting the final temperature of the brass. So TF minus TI. Well, actually, I know TI, the initial temperature, which is 20 degrees Celsius. Okay, there we go. So now we do 1,026,600 divided by 50,000. Okay, perfect. And then we do that answer divided by 0.37. Okay, and then we got, after that, 55.495 equals, okay, the final temperature minus 20 degrees. Okay, so all we got to do is change that 20 to the left side, and we end up with 75.495 equals the final temperature. Okay, so when I looked this up online, it said something like 27 degrees. I could not for the life of me figure out how they got to 25 or 27 degrees. All their numbers seem to be the same as the ones that I had. So, no idea. We'll see though. All right, hopefully that's the right process. We can memorize that. We'll just use that. All right, final question. What mass of aluminum in grams can be heated from 24.5 degrees Celsius to 44 degrees Celsius, by a quantity of heat sufficient to raise the temperature of 125 grams of water through this same temperature interval? So they make it pretty easy for us. They give us Q is going to be equal to the mass of the water, 125 grams, times the heat capacity of water, 4.184, times the change in temperature. Now we can figure this out. 44 minus 24.5 equals how much? Give it to me. There we go, 19.5 grams. What does that mean by G like that, man? All right, let's just check. 44 minus 24.5. That's right, 19.5, okay. Times 19.5. Okay, so once everything's in grams is in grams, Celsius is good. Okay, just checking. So 125 times 4.184 times 19.5 is 10,198.5. So Q is equal to 10,198.5. Now remember, this Q, right, is going to be the same heat that we're going to use to heat up an X mass of aluminum through the same temperature range. So 10,198.5 equals M, my mass, times the heat capacity of aluminum, 0.902, times the same temperature range, which is 19.5, and then we'll find the mass. So 10,198.5, and let's just do this one right here. 0.902 times 19.5 equals, let's see what we get, 17.598. And then let's do this one over here, 17.589. Did I say a completely different number just now? Sorry about that. So 10,188.5 divided by 17.589. Yes. And we get 2,898.971. Wait a minute. 19.5 times 0.902 gives me something different on the calculator. Oh, wait, hold on. It's because I did something different. 19.5 times 0.902. Okay. Now we got that the same. Okay. And then we got 10,000. Divided by interesting. Let's do it one by one. 10,198.5 divided by 19.5. That gives me 523. And then I divide that by 0.902. That gives me 579. What the heck is going on here? So interesting. Okay. Sorry, that was a complete derailment of the video. But let me just do that. Is that not the same? Am I? Okay. I think I did something weird. Nope, I didn't do anything weird. This thing did something weird. Okay, let's not use this anymore then. How do I get rid of that? There we go. That's the wrong answer, man. So if you put in your calculator 10,198.5 over 17.589, you should get 579.82. There we go. It must have been something wrong with this little calculation. Let me try that one more time. Okay, 10,198.5 divided by 17.589. Yeah. Okay, that was weird. Okay, never mind. We are in agreement. We're good. 579 grams. There we go. That was kind of weird. Sorry about that. Okay, that's it.